Hello, 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 and welcome back to L4.2. Some of you have a jump start. Some of you do not have a jump start. If you don't have this jump start, you have this cool picture, which makes the triangles and the monkey bars look like they're dilating away. It's pretty cool. And then it launches immediately on the project. So if you have that sixth period, I'm looking at you, you will just have to wait a minute while we do this jump start. Given that triangle RST is a scale drawing of ABC, therefore corresponding sides are proportional. Scale drawing. Okay, so they're similar. Find the missing side of each triangle. Okay, tricky. They've turned it over. Between the triple and the double is 6. Between the triple and the double is, I don't know. So that's a question mark so far. Between the double and the single arc mark is 8. And between the double and the single arc mark is 12. Okay. So 8. If we end up at the small one, divide where we came from. Is that the way I want to do it? Actually, I'm going to switch it around. Let's say we end up here. We end up at 12. We came from an 8. There we go. That's better because that's 1.5. And so that is the scale factor. So now we know that as 8 went up to became 12, 6 went up and became 9. And this, this one's going to be hard. Going the other way, we have a couple of options. We could divide by 1.5, because starting here, we're going to multiply by 1.5 to get to 6. So we could go backward by dividing by 1.5, or we could calculate the backward scale factor. So if we came down and ended up at 8 and came from 12, that is 0.6 repeating. That's annoying. Well, let's just call it 2/3. Okay, so now if we're going the other, since we can take 12 to multiply by 2/3 and hit 8, oh, that's kind of loud. Then we can start with 6 and multiply by 2/3 and end up here. So 6 over 1 times 2 over 3. 2/3 equals 12 over 3 equals 4. Oh, that was duh. That was okay. And I believe because it's upside down, there's actually a negative scale factor possibly. There actually might be a center of dilation here. This is extra credit. You're not supposed to know about this. Let's see if it makes any sense. If this is the COD, okay, and we're coming from. If this is the pre-image, and so we multiply by this length by 1.5, it becomes this length. Let's look at these millimeters. 28 millimeters versus 38 millimeters. That seems about 1.5 more. No, it's a little off, but if you just eyeball this, this is 1.5 times longer. This is 1.5 times longer. So the scale factor should actually be -1. But we don't learn about negative scale factors, so. Okay, thanks sixth period for hanging in there. Given triangle ABC. Let's read yours. Given triangle ABC, use point M as the center of dilation to locate the vertices of a triangle that has side lengths that are 3 times longer than the sides of ABC. And then second, use point N as the center of dilation to locate the vertices of a triangle that has side lengths that are 1/2 the length of sides ABC. So when we get to number 2, we're going to be going towards N to scale down half the distance to N, half the size to N. Right. So that's the same instructions here, although they call it A and B instead of 1 and 2. How bizarre. Which one do I want to use? Well, most people have this one, so let's go with this. 3 times rulers in the front. Okay, I like to use millimeters just because there's a lot of them. And it's fairly easy to use. Okay, 13 times 3 is 39. 39. So the nice thing is measuring from the center of dilation. You know, you don't have to move the ruler. You measured 13 millimeters to here, times 3 is 39 millimeters to here. Cool. Let's go to point C. Line up. I'm lining up this 0 line here with M. And it looks like it's 36 millimeters, right? 35, 6 to point C. 36 times 3 is 90, 100, and 8. So this is 100 millimeters, 10 centimeters. So there's 100 little dashes. Dash, 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 100, 105, 106, 107, 108, right? Oh man, sleeve caught. Bear 6, 7, 8. Am I still in line? Oh man. Oh, now that I've readjusted, looks like it's only 35 millimeters. Oh, that's going to change. So 105. Let's mark it. There we go. All that drama. Okay, last point. Point B. What is the distance from point M to point B? It is 43? 44. 44 times 3. 132. Double check that. 120 plus 12. 132. Okay, let's go with it. 130 millimeters. 132 millimeters. Okay. Now, that was A prime. I should have marked these as I was going. That was the first one we did. Then C got pushed out 3 times further, C prime. Then B got pushed out 3 times further, B prime. And now we connect the primes. And it actually is more accurate if you make sound effects. Da da. And now, that was 1. So now, it is time to scale factor down. Yeah, this will work. So 50 millimeters, so 25. You could put the 0. You could be putting the 0 on N. Whatever number you get, you just cut it in half and count off. So 80. Call that 80 millimeters. Go to 40 then. 72. Okay, that's not too bad. Half of 72 is 36. Oh, and I messed up. That was not. This was B prime, not N prime. And that's A prime. Let's get serious here. How can I clean this up? I think it's the smell of this ruler. It's making me woozy. Ask Mr. Mazeppa to open a window if you have a bunch of these vinyl rulers floating around. Okay, that triangle is the sides on this triangle are half. Whoa. The sides on this triangle are half the distance of the sides of this triangle. Don't believe me? Let's measure it. 30 millimeters. 15 millimeters. It's amazing. Now, label the vertices in the two triangles that you created in the diagram above. Based on this diagram, write several proportional statements that you believe are true. First, write your proportionality statements using the names of the sides of the triangles in your ratios. Then verify that the proportions are true by replacing the side names with their measurements measured to the nearest millimeter. Okay, well that brings up a whole brand new topic. Proportionality statement. Basically, we make a proportion, which is a ratio. A proportion compares two amounts, and then we make another comparison that is the same comparison. What am I talking about? If you compare 2 to 4, this is a new number we made out of two different numbers. And we can say that it is equal to 5 compared to 10. These are proportional, right? And if we multiply by 1.5, if we multiply 2 by 1.5, and we multiply 4 by 1.5, we will get to those two amounts. Let's try again. 2 over 4 is the same as 6 over what? Well, 2 times 3 gets you to the 6, so 4 times 3 will get you to 12. Okay, 2 over 4 is a half, and 6 over 12 is a half. These are proportionality statements. They're true comparisons. They make an equality between two comparators, also called ratios or proportions. So we're looking for proportions that are the same. If I weigh 100 pounds, that's 100 pounds, LBS. Thank you, Britain. I weigh 100 pounds. I eat 2 pounds of oatmeal. My kid weighs 50 pounds. And if they ate the same proportional amount of oatmeal, well, 50 is half of 100, so half of 2 is 1. He eats 1 pound of oatmeal to be proportional. And now we can write the proportionality statement. 100 over 2 is the same as 50 over 1. True facts. Okay, but what about this? Well, we know that if you compare the lengths of AC, remember in geometry when you write two letters, it actually stands for the distance between them. And if we compare it to A prime, C prime, well, that we know that this is actually going to be 1/3. The first one was, the second one's 3 times longer. The bottom one's 3 times bigger. But you want to know what else is 1/3? The distance CB compared to C prime, B prime. This distance here. These are all equal to 1/3. And let's test it. AC is 20 millimeters. And A prime C prime is 65. That's not 1/3. What happened? It's close though. Okay, look at that. It's not. Aha! Check that out. I measured wrong. This is 22. Now we're much closer. So much closer that we can just fudge this one and say that it's 66. Actually, it totally is 66. What was up with my measuring? Well, that's why you gotta check against theory. The theory is it should be equal to 1/3. And indeed it is. But don't forget the other ratio, CB to C prime B prime. Let's make sure that's also 1/3. 21? Huh. Maybe it's also 22. That's really boring if it's also 22. Yeah. I mean, it does look like it's maybe a little bit shorter. Maybe it was 21. 21 to 63 should be. Yeah, that side is close, but I don't want to deal with that. Let's see. Well, theoretically, right, AB should be the same ratio. AB to A prime B prime would be the same as these, comparing the different sides. So let's just throw that in there. Maybe that will work. 32. 32 times 3 is 96. Yes, that is what I like to see. 9, 95, 96. 30, what was it? What was the original one? 31? Wait, 31 times, 32. Ha ha ha. Great. What else can we say? Well, weirdly, if we take a side on the original triangle and compare it to another side on the original triangle. So I'm taking whatever number this is, this distance, and comparing it to this, getting a comparison, getting a ratio of that to that. But that has to be the same ratio as the big one, top side to this long side, because the bigger triangle is just 3 times bigger. So let's see, our original tiny triangle, top side is, what did we decide, 22? Didn't have to measure that again. And then I measured this already, it's 32. I hope. Yeah, let's call it 32. 22 to 32. That's awkward, I don't even know what that number is. If this was 33, nope, it's definitely not 33. Equals, now let's look at the big guys. 66, yeah, I already knew that, right? Compared to 95, 94, 95, 90. I'm going to go with even numbers here. Now, time to find out. .6875, 11/16, okay. 66 divided by 94, 33/47. Oh, so 0.7. So measurement's not exactly there. Wonder what went wrong there. Inaccurate on the measuring. Let's get this little one involved. If it's half the size, then okay, this top one should be 11, right? Because the AC we know is 22, and this is 11. It's actually closer to 12, but let's call it 11. User error. Well, actually, we know it's 11, so let's just use the theoretical value. So this is 22. This is 11. This is. I wish this was just 33. It'd make it so much easier. Oh yeah, let's do one of these where we compare it not to the other shape, but oh yeah, these are basically the same, right? So this should basically also be 11. Yay! So now we have AC compared with CB is the same as A prime C prime over C prime B prime. There, it's 22. Oh, I'm not on the screen. 22 divided by 22 equals 11 divided by 11. Those are both equal to 1. Okay, true facts. Let's do one more interesting one. Well, we could do, yeah, let's do. So remember, when we compare two sides on a triangle to the same two sides on a different triangle, we get the relative size between those two, which is 1. This is a 1-to-1 ratio here. It's a 1-to-1 ratio here. But when we go between, like this, A prime C prime compared to AC, which is what we're going to do next, A prime C prime compared to AC, and then we do C prime B prime compared to CB, running out of room here, C prime B prime compared to CB, we'll actually, because we're comparing sides that have been scaled, we will reveal the scale factor, especially because we're starting from where we end up, dividing by where we came from. So we end up at 11, we came from 22, that's where we started, and we came from 11, we started at 22, and these equal 1/2, which is the scale factor. And if this isn't what happened, but if we had actually started at the little one and grown up to the big one, then the scale factor would be 2. And we could flip these all over, 22 over 11. See the power of reciprocity, the reciprocal. Okay. All right, we got proportions. See above. Try to make one original proportion. One original proportion for you right here. Do not write this down. You're supposed to make a new proportion. If you write that and circle that, Mr. Mazeppa's gonna take off a point. Based on your work, under what conditions are the corresponding segments in an image and its pre-image parallel after a dilation? Oh no. I don't care about that. Yeah, they should always be parallel because there's no rotation. So AC and A prime C prime are parallel to each other. I guess if a side is perfectly in line, then it'll stay. It's always except. Oh, I'm way down here. Huh? Always except when a line segment is on a line that goes through the COD, the center of dilation. This is a great lesson, huh? And it's not even done. Give reasons for it. See previous. Okay, I'm not really that interested in the parallel thing. I mean, I guess it's cool. I'm much more worked up about these proportions. Given ABC, use point A as the center of dilation. Oh, with a scale factor of 2 to locate the vertices. Well, so this is interesting. A is the COD. This is kind of like the square in the definitions page from Friday. So it's looking like 31. Why isn't it just 30? Gets pushed out to 62. Is there someone out there? Oh, I'm talking to my kids. They're here with me today on a Sunday making this recording. Oh boy. 45, 40, well, let's call it 44. I like 44. It's one of my favorite numbers. And we'll push out to 88. Wow, we are in a different, we are over the instructions on the next problem. Hilarious. I love it when they do that. They're so funny. Who makes these things? Somebody. I appreciate them, whoever they are. So A did not move. The center of dilation is the one point that does not move when things are getting dilated. And explain how the diagram you created above can be used to prove the following theorem. The segment joining midpoints of the two sides of a triangle is parallel to the third side and half the length. Okay, well, yeah, if you think of so this is why they're calling it a midline. It is halfway between those two. Sometimes it's helpful to turn it like this. Yeah, people love that. You'll see lots of problems with this orientation. Now, we know that CB, well, actually, let's start where we end up at C prime B prime. So we end up at C prime B prime divided by where we came from, and we know that equals 2. So these are numbers. This divided by that is 2. Because this one's twice as big. This line is twice as big. If this line is twice as big, then this is half this one. Maybe we should have done it the backwards way and say, what is CB compared to C prime B prime? Well, let's measure. CB is 31. Oh, we already knew that. I think I measured that already. And this better be 62. Right on the money. And 31 over 62 is 1/2. So this is 1/2 as big. It is also parallel because when you dilate lines that, as long as you're not pointing at the COD, you get pushed out into your parallel. Why do they have to make us prove so many things at once? I don't care about the parallel thing so much as it's half the length. Nice. Halfway. Half the length. I think that's it. Are we ready for more? Oh no, it has been 27 minutes, so that is quite enough. Thank you very much. Have a great day, and I'll see you tomorrow.